Hey class, so I've already posted the review, so you should be able to follow along whenever we get to that portion. We'll do that once we finish the work on Chapter 9, which is Equivalence Relations and Partial Orderings. Yeah, I believe that's it. So there's not a lot left to the chapter. We will have made our way through about 3/5 of the course material after this, and within the first couple of weeks we should finish up with graphs and trees, and then we'll go back to the beginning, and hopefully we'll be able to find some topics that will allow us to thread everything that we've learned together, with an emphasis on algorithms this time around, as well as manifesting those algorithms into actual programs and or functions within programs, to kind of reinforce it. And then the third time around we'll focus more on the proofs themselves, and we'll still again we'll be touching on everything again, but hopefully by November everything should feel kind of comfortable and second nature, and you should feel really confident in where you are in the class. And if not, definitely feel free to reach out to me, and we will work together individually to try and overcome whatever it is your reservations about the course are. So let's jump into it, finish up Chapter 9, and then we'll go into the review. We will, as promised last time, discuss databases a little bit. It'll be very light. I want the middle third of the semester to really focus on the practical aspect, so algorithms, yes, but also some of these additional tools that we'll run into. So databases, which are going to be intimately related to any development work that you do, because there's always a persistence aspect to it, and developers will be asked to identify the data models that will be used and the relationships between them, and sometimes the developer has to do it on their own. Sometimes they work with a database administrator. It's possible that there's a really talented project manager that will help to identify the data for whatever given domain that you're in. But it's been my experience that it tends to fall to the developer to identify how the data all fits together. And so whether or not you're doing it directly, you are in essence defining the structure for the database. So it can be a little intimidating. Again, I didn't have a database class in my undergrad. It was an elective that I just never had the chance to to get around to. It wasn't until later on, whenever I tried interviewing for my second job, that I really became interested in databases, in part because I really needed to know it to get that second job, and then I didn't get it. I completely tanked the interview, and so it was in recovering from the embarrassment of the tanking of said interview that I really became comfortable with databases. So again, it may be something that you don't master before you graduate, but that's fine. Like so many aspects of this job, you won't actually master it until you're out there in the working world. But it's your ability to continue to learn and continue to add skills to your overall set of knowledge that will ultimately define how successful you are. Okay, but that's all down the line. We have plenty to cover this semester. For now, let's finish this up, and we'll go over the review, and then you can start to relax going into the weekend, confident that the exam next week will be a piece of cake. Okay, so equivalence relations. This is a term that really confused me whenever I was an undergraduate, because equivalence, whatever. Like, are we saying equivalent statements or whatever? And not exactly. So again, to help motivate the material, there's a concept known as sharding a database, or to implement a a distributed database model where your data is split up across multiple servers, and none of the servers actually share any particular information. So again, just introducing a new term, there's this concept of multi-tenancy. So if you're a software as a service company, then it's possible that you have multiple customers that really don't relate to each other in any particular way. So there's no specific imperative, there's no need for that data to all live in a single database. It's possible to split it out. And relational databases will tend to perform pretty well until you get up into the millions of records. And then it very much depends how you organize your data. And even if you're doing everything in a prescribed manner, so if you are using primary keys and foreign keys to relate tables to one another, and you're maintaining it properly, it's still going to eventually hit this point where you start to notice lag every time you make a request against it. And if you get to the point where you have that many customers and that much data, then there are going to be even more requests. So the problem kind of compounds on itself. So not only is it slower per request, but you get more requests per minute, and so the problem kind of feeds on itself, and it can kind of run away from you. So one of the solutions that Google made really popular was to break the data up, and they used this paradigm called shared nothing, where they identified the data that didn't necessarily need to live on the same computer, and then they made these reliable methods in order to figure out, well, which server needs to take which request based on whatever, right? And so in a multi-tenancy application, so something that serves many customers, if the customers don't have any shared data, then all of the data associated to that particular customer needs to live together in this unit, right? This per customer footprint that has to live somewhere, and that has to stick together. But so long as it all sticks together, it can live on any individual computer. So you can use whatever algorithm you want to assign that data to a particular server, and then you can spread it out pretty evenly to any number of machines. And so again, you might call it a distributed database, you might call it a sharded, like as in shards of glass, a sharded database. And so coming back to this, the equivalence relation, right? So this is the formalism of that concept. So how do you identify what data needs to live together? And even if you have some more complicated design where your customers do actually share data sometimes between one customer and another, then the situation gets a little bit stickier. But you can use some formal structure like this, an equivalence relation, to identify what data lives on the same machine. And so in that case, the equivalence is that it lives on the same machine as some other piece of information, right? So it's it's still a little abstract, and it's definitely really far away, and even several years into my career, it was it wasn't explained to me in these terms. The response I got whenever I suggested it was, it's not so easy or whatever. But it can be done, and this is the concept that I want you to think about if you ever come across that problem, defining this equivalence relation. So it's more than, does A equal B? It's does a particular thing have these properties that whenever it's related to something else, right? Okay, so in the case of a sharded database, so you might ask if a customer's record lives on the same machine as itself, and it does, right? By, hopefully, if you've implemented it right. So in that case, it's reflexive, so it identifies with itself. Is it symmetric? So if it relates to some other record, then it doesn't matter which order you ask, right? Is A related to B, or is B related to A? If it always comes back indicating that they do live on the same machine, then you've satisfied that symmetry condition. And then is it transitive, right? So if you have 3 records and you have that record A lives on the same machine as record B, and record B lives on the same machine as record C, then record A lives on the same machine as record C, right? And so if you've satisfied that, then you've created an equivalence relation. And so again, we would have to go into a more specific example for, I think, this to gain greater purchase in your mind as terms of what exactly it is that we're talking about. But if you've satisfied those 3 conditions, then you can do some advanced work like breaking up a database, and that is a very non-trivial step in the growth of a company. And so I understand that's a difficult thing to think about, but it's also a difficult thing to think about for people several years into their professional career. So I wanted to introduce the concept to you now to give you kind of time to think about it as well, right? But if you ever come across it, then an equivalence relation is really more than just the answer to an equivalence statement, right? Like, does A equal B? It can be more than that, right? If you're talking about database records, then you can define an equivalence relation if it satisfies these 3 properties. Okay. So then, A and B are equivalent, yada, yada, yada. Okay, and so again, using the sharding example, so they're equivalent in that case, right, they satisfy the equivalence relation. They're equivalent in terms of representation if they lead you to the same host machine, if their information leads you to a particular server. Okay. So equivalence classes. In the case of a sharded database, the equivalence classes would be the different servers. So they are of an equivalence class if they live on the same server, if their information lives on the same server. But in terms of understanding what it is that we're talking about, I think it's easier to think about the modulus operator, and we'll use that as an example here, right? And so if you divide an integer by some integer greater than or equal to 2, right, then you will get one of n possible results, right, where n is your integer. And so it'll either divide in evenly, or it'll leave a remainder of 1, or it'll leave a remainder of 2, or it'll leave a remainder of 3, and so on. It'll never leave a remainder of n, because if the remainder is n, right, if it's the same as the number that you were dividing, well, then the remainder is 0, right, because it divided evenly into that integer one more time, right? So it's one of those things that it feels like we'll never use, but whenever we discuss encryption and RSA encryption in particular, we're going and if we go through and prove it, then you would see that we rely heavily on modular arithmetic, and modular arithmetic is it's the modulo operator, right? It is just explicitly dealing with these remainders, and so it seems like this very fundamental thing. Well, long division, and you have some whole number of times that it divides in, and then you have some remainder. It doesn't seem all that interesting. But again, the fundamentals of encryption on the web are built on this very topic, right? So equivalence classes are essentially just everything every integer breaks down into leaving some remainder whenever you divide by some number, right? In this case, 4. Right? So either remainder is 0, 1, 2, or 3. And then, all of the infinite number of integers fit into one of those 4 equivalence classes. So that's what the topic is. And so members of an equivalence class are known as representatives. And so typically you would take the principal member of the equivalence class to represent it, right? So in the case that you're dividing by 4, 0 would be a representative of this first class, and that would be the class where in this case 4 divides evenly into that number, or where it's a multiple of 4, however you want to say it. 1 would be an example of another representative of the equivalence class, and so 2 and 3, but really you could choose any from the set, but typically you want the representative to imply something. So in this case, we would choose the representative to equal the remainder whenever you divide 4, in this case, into that number, right? So if you divide 4 into 9, it's going to leave a remainder of 1. So you would just talk about the class of 1 modulo 4, right? So again, it's not this earth-shattering math or whatever. It's learning the jargon essentially to kind of discuss these higher level topics. So if it feels like overly simple, or you think that you're missing something or whatever, no, it's just definitions. It's just new ways to describe the stuff that you learned whenever you were discussing long division. But I can tell you, RSA security will be built on this concept, and you can come up with these very advanced results, these very significant results, once you kind of build up the language to discuss the problem. Okay? So it's equivalence classes and representatives, and then the congruence classes, modulo M or whatever. So it's just the same thing, right? So you can discuss, like, it doesn't have to be 4, so here we use M instead of N, right? But you can discuss all of the different classes, right? So here we've taken this where we explicitly state each of the equivalence classes, and we've shortened it, right? So the remainder in this case is A, right? And the number that you're dividing by, or you're taking the modulo of, is M, right? So this is just another way of writing this, but instead of starting with a specific number, we just start with A, and then the pattern kind of fits from there, right? So you have A, and then it's plus or minus M from A, and so forth. And so if you see, like, if you plug in A equals 0, 1, 2, and 3 into this formula, and M equals 4, then you'll see that you can construct each one of these explicitly from this form, right? So this is just a condensed way of writing all of this, right? So to do it in one line, or in a symbol, instead of explicitly, right? So that's all we're doing there. Okay, so now we have a theorem. Let R be an equivalence relation on a set A. These statements for elements A and B of A are equivalent, right? So A relates to B, right? So that should be a lowercase a. I'm terrible. Okay, so A relates to B. The equivalence class of A, or the congruence class of A, is equal to the congruence class of B, right? And so again, we've shown how A doesn't necessarily have to equal B, right? Like here, we chose 1 because that was the remainder, but we could have chosen 9 as a representative, right? So so it's possible that they are of the same equivalence class, but that the values A and B are distinct, right? So I want to distinguish in your mind equivalence, right, like being equal to, like explicitly equal to, is distinct from belonging to the same equivalence class. So whenever you discuss modular arithmetic, all of these numbers, everything in the set, is equivalent to 1, right? But they're not necessarily 1 themselves, right? Before you take the modulus, or before you seek the remainder. Okay, so we're just saying that these are equivalent ways of stating the same thing. And then the intersection of this class and this equivalence class is not equal to the emptor set, right? And so this is actually kind of an interesting result from abstract algebra. And so it's a whole lot of build-up. Abstract algebra, the entire subject, is kind of built around group theory and so forth. And it's just all of the advanced stuff that you can think of in terms of division. Oh, I'm sorry. Here, let me zoom in. Right. Okay. So yeah, this. All of it is just essentially starting with this really large group for a set of elements and the actions that you can take on it. So the root in all of this, or the top level of the latest, would be the symmetry group, or the permutations on a set of n elements. And then all of the other interesting groups, all of the other interesting ways that these elements interact, such as like rotations of polynomials within vertices, and then rotations and reflections and so forth. They all, the number of actions that you can take on them that follow these certain rules, are all perfectly divide that symmetry group, right, the permutation group. And so it's interesting that each time you come up with some simpler subgroup or whatever, that it perfectly divides into the parent group of operations. And so there is that perfect division, and whenever they are members of that same subgroup, right, then the set is empty, right? They have the same size, and it's this non-empty subset. And then there's all of the congruence classes, right? So, if our parent group had 10 members and our subgroup has 5, then there only half of the actions were valid in that subgroup, right? But the other half, like, what was that, right? And so it's this kind of, it works fine in the parent group, but in the child group, once you've broken it down into some smaller set of rules that are observed, it's the kind of broken operations, and there's rules around how many sets of broken operations there are, and what members can be in there, and the fact that they're all the same size as that subgroup, and so it's just really interesting, kind of the way it all plays together or whatever. But that's all. If you ever encounter it in your academic career, it's still a ways off. But we will discuss it a little bit. Anyway, so these are all just equivalent ways of stating the same thing, that A and B are of the same equivalence class. And just note that this should be a lowercase a. Okay. So a partition of a set S is a collection of disjoint non-empty subsets of S that have S as their union. So again, it's the concept of disjoint sets, right? So you can think of a partition as like a parcel of land, right? So a county has a fixed amount of land. It divides it up into even partitions, and no two people that buy these parcels of land have overlapping territory. They're all given non-overlapping parcels of land, and you can do the same thing to sets of numbers, right? Where you break it up and no one has the same amount of numbers. You can do it to, as we were discussing earlier, databases. You can partition your database so that none of it overlaps. Yeah, so this is just, again, this is a definition, it's not a theory or whatever, but we say that if you break it up so that you have non-empty subsets, but you break it up and it's disjoint, there's no overlap, and then whenever you glue it all back together, you have that original set of data, then you can call it a partition, right? Those broken down elements. Okay, so let R be an equivalence relation on S. Then the equivalence classes of S form a partition of S. Conversely, given a partition A sub I such that I is in I of the set S, there's an equivalence relation R that has the sets AI. This is equivalence classes. Okay, so yeah, this is kind of what I was saying earlier. So you have, like whenever you divide some set S, it breaks up evenly, right? So if you were, I mean, this really isn't anything in particular or particularly interesting. So let's say you have 60 elements, right? And you break it up into 6 partitions. Then you have 6 sets of 10, right? And none of them overlap. That's basically all that we're claiming, with this theory here. So I need to include an example to make it a little more interesting, but that's essentially all that we're saying. So here AI would be your sets of 10, right? And I is that 0th set, first set, second set, third set, fourth set, fifth set, and in total that would be 6, right? 0 through 5. So yeah, it's just saying this is either A0 through A5, and then whenever you glue them all back together, you get that original set of 60 elements. Okay, and so that would be where it's partitioned by an equivalence relation, right? So in that case, those 60 elements, if they were numbers, the numbers, 0 through 59 or 1 through 60, it doesn't matter. If you broke it up by taking the modulo 6, right, then each of those sets, the set where there's a remainder of 0, the set where there's a remainder of 1, up to a remainder of 5, right, they would all have 10 members, right, and each one of them forming an equivalence class. Okay, partial ordering. So a partial ordering is reflexive, anti-symmetric, and transitive. So if you think of a matrix is symmetric, right? If the value at row I, column J, is equal to the value at row J, column I, right? So it's got this symmetry along the about the main diagonal, right? So anti-symmetry says that well, it's always 0, right? Like it's if they are equal, right? So if row I, column J equals row J, column I, then it's because they're both 0. Otherwise, they're not equal. It can be anything, and the only exception to that would be if it's on the main diagonal. So if I equals J, right, and it's along that main diagonal. But it does have the other properties of an equivalence relation, right? So reflexive and transitive, but anti-symmetric. Right? So that's partial ordering. Okay, so it's a set together with a relation, right? Can give you a partially ordered set, or poset, which you'll never hear me say. It is given by the same notation, right? So the set and then the relation. Members of S are called the elements of the partially ordered set. Right? Okay, so the greater than or equal to relation is an example of a partial ordering, right, on the set of integers. So it's equivalent, right? So if A is less than or equal to A, right, then you have equivalence, right? The anti-symmetric requirement is there, right? So if A is greater than or equal to B and B is greater than or equal to A, well, that only happens, you can only have these at the same time if A is equal to B, right? So that's anti-symmetry. And then the transitive requirement, so A greater than or equal to B, B greater than or equal to C, implies that A is greater than or equal to C. So greater than or equal to combined with the set of integers makes a partially ordered set. Right? So Zahlen, integers, right? German for integer, or number actually, and greater than or equal to. Okay, so it's a note on notation, right? So it's this not quite less than or equal to sign. It's got these I guess you'd call them duck lips. I don't know what else to call them, but it's got that curved less than or whatever. Right? So for some arbitrary partially ordered set, right? This is just some generic symbol. It doesn't mean less than or equal to. It's a placeholder for a relation that satisfies this partial ordering. Right? Okay. So then elements of A and B are comparable if either A relates to B or B relates to A. Right? When A and B are elements, and if they don't relate, then they're called incomparable. So do we give an example of that? No. Okay. Well, I mean, earlier in the semester we kind of talked about how, if we were to rank like knowledge or whatever, you would expect the knowledge of a first grader to be completely contained in the knowledge of a first grade teacher. And so in that sense, you could say that they have some subset of knowledge with respect to that particular teacher. And I guess because they're so young, right, you would also expect the knowledge of a first grade student to be less than or fully contained within the knowledge of a basketball coach. Right? But you wouldn't necessarily compare the sets of knowledge between that first grade teacher and the basketball coach. So you can relate the first grader to either one of them in terms of what they know in the world. But you can't necessarily rank one against the other whenever you're talking about basketball coach versus first grade teacher, right? Like they're not really comparable. In that case, it's apples to oranges. Okay. So total ordering, right? If a partially ordered set and every two elements of S are comparable, then it's totally ordered or linearly ordered. And a totally ordered set is called a chain, right? So an example of a totally ordered set is if the set of integers, right, is actually totally ordered. So it has that anti-symmetry or whatever if you do this operator, but if you change this from greater than or equal to or whatever, if you use the less than sign, like strict less than instead of less than or equal to, then the elements never really compare to themselves, right? Like you've gotten rid of that. So you just don't have any repeats. If you have a distinct set of elements, then you would never really compare it to itself, right? And then you would have the, I guess, anti-symmetry, right? But in the fact that you would again never have equivalence because the set of elements are distinct, right? So in that case, you're really down to just the transitive, right? So if we're using the greater than example, strictly greater than, A greater than B and B greater than C means that A is greater than C, right? So 10 is greater than 5, 5 is greater than 1, means that 10 is greater than 1, right? Okay, so that's totally ordered. So everything is related, like you can compare everything directly to some other element, to any other element in the set, actually. And so that's totally ordered. Let's see. Okay, and so well-ordered is a particular kind of totally ordered set. In particular, it has, so for every non-empty subset, finite subset, it should say, but it doesn't, S has some least element. So that means that it's behaving correctly, right? So you would say, okay, well, when wouldn't that be the case? Okay, well, the set of rational numbers, like so fractions and decimals and everything, right? That has a like it's totally ordered. You could pick any number between -1 and 1 and compare them to one another, right? And they would tell you that one number is larger than the other. But if you were to take the open set, right? So every number between -1 and 1. Well, if you took away those boundary numbers, right? So -1 and 1 specifically, and it's just everything in between them, there is no number that's next to -1, right? Like you can always find some number that's halfway between whatever number you suggested and -1, right? So there is no least element in that set. So it's not, that would not be an example of a well-ordered set. So it's totally ordered, but again, because it's not this finite set of numbers that you're operating with, you can't pick out the least element, right? Like it's open. It's yeah. Okay. So then well-ordered induction, right? So suppose that S is a well-ordered set, and P of X is true for all elements in that set. Then if for every element in the set S, we have that P of X implies P of Y, right? So some proposition on X implies some proposition on Y. Okay. For all X that relates to Y, right? So you're going to see this a lot just in theorems in general or whatever, right? Where you're trying to figure out what it is that's exactly saying, right? So I want you to think of this whenever you see a number or some variable in parentheses and something that precedes it. So this is some constraint before you plug it into the function, right? And this is some constraint after you plug it into the function. Okay, so this is basically saying that some proposition on X is true for every element in our set if we can say that that it being true for X implies that it's true for all Y, right? So if we can say this whenever X relates to Y, then it's true for all X in the set, right? Okay, so an example, right? We're talking about induction here. Whenever we use induction in our proofs, then we make some claim based on initial conditions, and then we say, well, for all integers k that are larger than this, or integers n, or whatever variable we choose, then it holds true there, right? So we have that base case, and then if it's true, for every number larger than that, right? Then or if we can prove it inductively, right, then it's true for every number larger than that. So what we're saying here is that we don't have to start with A0 or A1 or whatever. We could start with A10 or A20, and it would be true, for every y that's greater than it, right? So again, this doesn't necessarily mean less than, right? But relates to. But in the example, and this symbol was chosen because that less than operator is so prominent, right? So in the case of induction, it does mean less than. So then, if we can say that it's true for all y that are greater than whatever we chose for x, right? Then it's true for any x, right? So for any starting point in our set of integers, if S is a well-ordered set. Right? Okay, so lexicographic ordering is an example here, right? And so, right, so we used induction in the case of integers, and so this is an example that we can use, like, that we can guarantee some ordering regardless of, however many inputs we use, right? So, this is terrible. Okay, so in this case, A1 cross A2. So you can think of A1 and A2 as being the alphabet, if you want, right? So then this is 26 letters, and this is 26 letters. And we can compare them, right? So you have the first letter and the second letter, and the first letter and the second letter here, right? And so, so we compare the first letters first, and that will give us an ordering. But if they're equal, right? If the first letter is equal to the second letter, then you compare the second letter, right? And so that's alphabetic ordering, or more formally, lexicographic ordering. And so you can use it again on more than just the alphabet. You can order, any tuples in that manner. Okay. So upper bounds, yeah. So if you can say that everything, you can think of this as less than or equal to in this case, right? But it's the generic relates to, right? So if every other element in the set is less than or equal to, or whatever equivalent relation we're using is, then U is called the upper bound, right? So if there's some last element in the set, then it's the upper bound. And then here, the lower bound, right? So if there's some first element in the set, then it's the lower bound. Okay, so those are pretty self-explanatory. You're already familiar with those concepts. So least upper bound, right, would be, and in this case, it may say that it has to be within the set or whatever, but not always, right? So we're talking about the open set between -1 and 1 being totally ordered but not well ordered. Okay, so that's an example where it has, -2 would be a lower bound on that set because it's less than every element in the set, right? But the greatest lower bound, right? So the largest number that satisfies the condition of being a lower bound would be -1, right? Because that bounds every number in the set, and there's no larger number that can claim to bound every number in the set below, and there's no and -1 is larger when it's greater than all of the other alternatives that can make the claim of being a lower bound. So in that sense, it's a greatest lower bound. And least upper bound is the other thing, right? So 1 bounds from above every number in the set, and it's the smallest such number that can make that claim, right? So that would be a least upper bound. Okay. So then latest, sure. Partially ordered set in which every pair of elements has both a least upper bound and a greatest lower bound is called a latest. And so it's, again, the key is that it's partially ordered set. Okay. Total ordering with this less than or equal to, or this placeholder, right? This relates to operator, is said to be compatible with the partial ordering R if A relates to B whenever A relates to B. Okay, sure. Okay. Okay, perfect. So what does compatible mean? Right. So you can think of like you're not always dealing with necessarily the same sets. So we've discussed like integers being like they are a subset of the rational numbers, which are themselves a subset of the real numbers, which are themselves a subset of the complex numbers, which are themselves a subset of quaternions, which are a subset of the octonions, and so on and so forth, right? So complex numbers don't necessarily permit an ordering, right? So even though they're this greater set of numbers, they're not necessarily compatible in terms of comparison. You could try, right? Like you could use something like lexicographic ordering or whatever, but it's not going to be as clean as you want it to be, right? So, but in terms of compatibility, you can use that same less than or equal to operator that you use for the integers on the rationals and the real numbers, right? So in that sense, it is a compatible operator on different sets, right? And then anytime you compare, an element that happens to be in both the integers and the rational numbers, right? So you compare it here in the integers and you compare it here in the rational numbers, you get the same result, then it's a compatible operator, right? So that's an example. Okay. Every finite non-empty partial order set has at least one minimal element. Okay. Yeah, so you'll see like the latest structures and stuff like that, and I should have given an example here, right? Because I said the minimal element is not the same as a globally minimal element. But whenever you're dealing with the latest, right? So you have this concept of up and you have this concept of down, right? To represent like something that resembles less than and something that resembles greater than, right? So up is greater than and down is less than. And so it more resembles a graph than a tree, right? And so as you go down, it's not necessary that there's only one element at the bottom of this lattice. There can be multiple, we'll call them leaf nodes, right? There can be multiple vertices at the bottom of this lattice that don't relate to each other at all. And so what this is saying is that if you take some subset of the lattice, there's always going to be some item that sits at the bottom, however you break it down. Yeah, that's it. But it's not necessarily going to be some global minimum. It just is a minimum. Okay, so we'll pick up after the exam on graphs. I want to take some time to go over the review, and we will, for a moment, discuss databases and so forth. Okay, so review. Okay, so whenever you get your exam, you'll get the TeX file and the PDF. Again, I'm encouraging you to do it in LaTeX because there's a 5-point bonus for doing that. But it's not strictly required. So, if you don't got to do it, right? But I would encourage you to do it, right? So you'll find student name, right? So human student would be your name, right? Copy and paste the TeX if you're going to go that route, and put it into Overleaf, and then as a human student, complete the exam, right? Okay, so the review is already posted, so you can do this along with me, or if you want to wait, I'll post the solutions as well. and you can try it on your own and then compare yourself against the solutions, or if you want to work along with me, you can do that. But I definitely want you to learn LaTeX. I feel like it's there is advantage in learning it, and so, but I don't want you to be intimidated as well, right? So that's why I want to go through this with you. And then in addition, right, the material as well, right? So there's always that the domain knowledge, which is in this case the discrete math, and then the trade knowledge, which in this case is LaTeX, right? So you're always going to be learning on multiple avenues. Okay. So we have recurrence relations, right? It says, is this a solution? Well, recurrence relations are supposed to give us initial conditions. Where are those initial conditions? Well, in this case, if it's a solution, then we can use the function to generate them, right? So generate initial conditions. F0. Well, actually, I want this. I like to use math mode whenever I'm doing this. So begin line. Yeah, it's helping me out. Okay, so F0. We're plugging it in, right? So it's F is n squared in this case, right? So it's 0 squared, and that's 0. And then we need, yeah, it's just first order, right? So all we need is that first term. So then we need our first term from the equation, from the function, right, the closed form solution, and then we need our first term from the recurrence relation after the initial conditions. And then if those are equal, then we have our base condition, we have our base case satisfied, and then we can ask induction whether or not it's a solution, right? So then test the base case. And actually, I want this in a new paragraph. Okay, so then A sub 1 just to be explicit. So that's 0. And then that's actually A sub 0 as well, right? Okay, so then A1 is equal to 1, right, because that's in. So we'll put that in parentheses to show that it's an algebraic substitution, plus A sub 0, right, which is 0. So again, it's another substitution. So we'll do that. So that's equal to 1. Right? And then f of 1, right, where n is 1, is 1 squared, which is 1. Right? So the base case checks out. So then we'll use the inductive hypothesis, right, to declare that, yeah, I think that if we went all the way up to some number k, right, and so at the beginning k is just 1, that's all we've shown it to be, right? So if we go up to some number k and it holds true, and it's held true at least to k equals 1, then we can get to k plus 1, and that would give us n equals 2, right? And n equals 2 with k plus 1 would give us n equals 3, and so on and so forth, right? And that's what we try to show with induction, right? But first we assume that it holds true for k, right? So a sub k is equal to what the function claims, right? K squared. Yeah, I'll do it here. Okay, so then we say, well, let's, we use the recursive formula, and we show that we can recover the closed form solution for k plus 1, right? So the terms of the sequence are given by the recursive formula, so we start there. And we've assumed that we have at least one example of this, and we've done more than assumed, we've proved that we have one example of this, right? So we assume that if it holds up to some value k, then we can get a k plus 1 term of the sequence that's of the form of the closed form solution, right? That's the whole principle of induction. Okay. So then it's the recursive form, right? So k plus 1, so whatever's here goes here, right? That's our value n, plus a sub k, right? And so we still have k plus 1, but now we make our substitution, right? So we've assumed that we had something here, and so we have something else that we can plug in for a sub k. Right? So let's do that, k squared. And then if we simplify, we have k squared plus k plus 1, right? Yeah, so this does not hold, right? So we'll say, okay, but that is not equal to k squared plus 2k plus 1, which would be what we were trying to show, right? K plus 1 squared. Hence, is not a solution. Okay, so I highly recommend that you test your results, right? And so we're programmers, so we can do that pretty readily. Let's break this out so that we can work on it over here. Right? So let's define f. So f is some function which takes an input in, and it spits out n squared. Right? And then a is also like the terms of the sequence, but we'll define it as a function. And this also takes some value n, right? And it has some initial conditions. Right? So if n is equal to 0, then we return 0. We just explicitly state the initial conditions. And then for everything else, we use a recursive formula, right? So we return n plus a n minus 1. Okay? Okay, so f of 0 is 0, f of 1 is 1, f of 2 is 4, and f of 3 is 9. Right? A of 0 is 0, a of 1 is 1, and a of 2 is 3, right? So we've tested explicitly, and we could have done this without using induction, but I do want you to use induction, that these don't generate the same sequence, right? So we proved it using induction, exactly as the instructions indicate, right? But we've also verified that, through testing, that they're not the same sequence, right? Okay. So that was a bit of a tricky one for a review, right? Okay. So now let's go into this problem. I'm dealing with the solutions now, so I'm going to reduce this to just 1 centimeter of vertical space. So close that gap a little. Okay. Okay. So we have some natural number, right? Some integer that's greater than or equal to 1. Some people define the natural numbers to start at 0. I will vacillate on that, right? Sometimes it's convenient to let it start at 0. Sometimes it's convenient to let it start at 1. But I assert that they are always non-negative. Okay. So again, we have some function f of n. It's of this form now. Is this a solution to the recurrence relation? Blah, right? Okay. So we will test it, using our skills later to make sure that we give the right answer. But let's try to use induction first. Okay, and then these all follow a very similar pattern, right? Like all of these induction problems. So we can just kind of copy our work and then substitute the values as we go. So we don't know the answer just yet, so we'll delete that. So we need initial conditions again, right? And it's first order, so we only need 1. So for f of 0, this time we have n squared n plus 1 squared over 4. But we know that n is 0, right? So we can plug that in. So then, well, we don't even need to do that, right? We know it's 0 because it's 0 squared, right? So 0 times anything is going to be 0, right? So we have that our first term is 0. So then we need to test the base case, right? So a1 is given by n cubed, right? And in this case, n is 1, right? Plus an minus 1. And so that's a0, right? And that's 0. So then again, we have 1. And then if we plug 1 into our function, right, our closed form solution, our proposed solution, then we get one squared is 1 plus 1 times 1 plus 1 squared over 4. So this will be 1, and this will be 2 squared, which will be 4. So 4 divided by 4 is 1. So there again, equal for the base case. Right? And then the inductive hypothesis. Right? So we've proven the base case. So now we assume that it holds true up to some integer k. Right? And so here we say that, well, it held true in this form, in the closed form solution up to that value. So k squared k plus 1 squared. Right? And then we try to show it to the k plus 1. Right? So we use the recursive formula, and we try and recover that closed form solution. So we've incremented using recursion, and we want to show that if we apply the inductive hypothesis, that it is again in that closed form solution, or that it's not, as was the case previously. Okay, so Okay, so the recursive form as k plus 1 cubed, right, plus a sub k. Right? So that would be k plus 1 cubed, and a sub k was this, right? And let's get rid of this so that we're not confused with where we are. Okay. So now we have to multiply some stuff out and clean up the arithmetic a little bit, right? So let's do that. So here we have k cubed plus it's going to be something k squared, some coefficient times k squared plus k, and then 1. Right? I want to say it's, let's see, k times 1, k times 1 times k, and then 1 times k times k. So it's going to be 3k squared and 3k. And then we have that fraction from above. Okay. But let's go ahead and multiply that out. Right, so then that would become k cubed. Oh, whoops, hold on. It's squared over here. Right, so this would be k squared plus 2k plus 1. Right. We'll pull in that k squared next time. And so we have to get a common denominator. So we'll multiply times 1, but in the form of 4 divided by 4. Right? So we get the common denominator. Right? So now we have 4 times this over 4. And then here we have that. But we wanted to pull this in, right? So everything in the parentheses gets multiplied by k squared, right? So we're distributing this. So now we get that k to the 4, k cubed, k squared, right? All over 4. Okay, right? So now they have a common denominator, so we have one fraction. Okay. And we're just doing addition. Right? So okay, so I'll look over here to figure out what needs to go in the numerator over here. Right? So here, the k to the 4 goes first. K to the 4 plus the k cubed terms go next, right? So there's 2 over here, and there's 4 over here, right? So that's 6 k cubed, and then the k squareds go next, right? So there's 12 over here, 4 times 3, and there's just k squared over here. So 13 k squared plus 12k plus 4. Okay, and so we know that we want it to look like this, right? So then it would be k squared, right? Like we can see, right? So we'll we'll elide the results for now, right? And we'll see whether or not it becomes what we want it to look like. So that would be k plus 1 squared and then here it would be k plus 1 squared, right, all over 4. So if it goes well, it'll take that form. And if it doesn't, then we'll have a statement that says that they're not equal. Right? So expanding that, we have this. It's really k plus 2 squared, right? K plus 1 plus 1, it's just k plus 2 squared. And then here, that k plus 1. So we'll expand both of those, and so then we get k squared plus 2k plus 1. Okay. And over here we have k squared plus 4k plus 4. And then if we multiply those together, we would get k to the 4 plus, oh god, y. Okay, so k to the 4 plus 4k cubed, plus 4k squared. Right? And now we distribute this one, right, the 2k. So that's 2k cubed plus 8k squared plus 8k. And then we distribute the 1, right? So it's just this. And so we'll just copy that last one. Okay. So now we combine all the like terms, right? So all of the k cubes. So there's just those 2 additional, right? So it's 6k cubed. There's 4 plus 8 plus 1, right? So it becomes 13k squared. Uh, 8k plus 4k is 12k plus 4. So this turns out to be exactly equal, right? So we're able to work forward to simplification and then work backwards to show that they were equal. I wouldn't call it a nightmarish amount of arithmetic, right? But there's plenty, right? So we showed that it does stitch together, right? So hence, it is a solution to the recurrence relation. Okay, so again, let's take the time to verify. Okay, so we have in this case f is again a function of n, right? And it returns n squared, squared times n plus 1 squared, right? All of that divided by 4. Okay, a is a function of n, right? with some initial conditions. So if n is equal to 0, return 0. Otherwise, return the recursive formula, right? So n cubed plus a of n minus 1. Okay, so f of 0, f of 1, f of 2, and f of 3. A of 0, a of 1, a of 2, and a of 3. Okay, so our manual testing appears to agree with our inductive results, so it does appear to be a solution, or we have proven it to be so. Okay, so let's reduce the vertical spacing again and complete this one. Okay, so then, well, we've already done it a couple of times, and I want to say that this might have been one of your homework problems, but maybe not. I might be mistaken. But I've already given you a couple of examples on how to do it, and you'll see it in the solutions whenever I post them. But if you haven't tried any of them so far, give it a shot, right? So it'll follow that same formula. So let's jump ahead to the counting examples. Okay, so this one is a constructive problem. You actually have to construct the recurrence relation and then give a solution to it. Right? So you have to think a little bit here, right? So when n equals 0, there are no bit strings. When n equals 1, there are 2-bit strings. Neither of them contain consecutive zeros. And then when there are, when n equals 2, our field splits, right? If our string ends with a 0, then we have to add on a 1, right? Then it is a solution only when we affix a 1. If our string ends with a 1, then either a 0 or a 1 will again be a solution. Okay. We might need more space. Okay, so then we can already see that there's two cases, right? So as we look back, we'll have to split them, right? So our solution, our relation will take the form of terms which of strings which end in a 1 plus those which end in a 0. Right? Okay, so then let's see. So for a given length, and let a sub n minus 1 represent the strings of length 0, or sorry, of length n minus 1. Okay, and ending in either a 0 or a 1. Right. And a sub n minus 2 represent strings of length n minus 2 which terminated with a 0, right? And so we can so we have that this number, the ones that end in a 0, right? They can end in either a 0 or a 1. It doesn't matter. If we tack on a 1 to this one of length n minus 2, and then it can have whatever length. And then these, if they were a solution at n minus 1, then we can tack on a 1. We can always tack on a 1, but then right. I guess, sorry, this should be ending in a 1. Right? So it ends in a 1, right? And over here. So we can do whatever we need with those, right? And then the n minus 2 would end in a 0, and then we could add a 1, and then a 1 or a 0. Right? So it ends up taking the form although I didn't quite set that up correctly. I know that it ends in this, but I'm going to have to choose a different type of constructed problem. But anyway, so this one does actually end up mirroring the Fibonacci sequence if you set it up correctly, which I have not. Either way, so let's jump ahead to the Fibonacci sequence. So this one you'll work on, and you'll use the characteristic equation. You'll find the roots, and then you'll solve for alpha 1 and alpha 2, just like on your homework assignment. The same thing here, right? So characteristic equation, and then solve. Relations, right? So you have some table, and then you have some selection condition, right? So for this one, I've actually set it up in SQL so you can see, right? This is how you would create the table. This is an example of inserting into the table. Not every language, I believe, will allow you to make multiple inserts using this syntax, but this one did. And so you can select all of the records from a table, select star from there. We don't have a particular test condition. And so here we do have a condition where we're selecting, right, where GPA is greater than 3.5. And so the tuples, right, the correct response, so list the following 4 tuples. And so here I have student ID, student name, major, and GPA. Right? So let's change that. So we're not selecting star, we're not selecting everything. Star is a placeholder for everything. We're selecting 4 tuples. So it's everything except for the student, the email, right? Oh, I would have expected it to give me an error, but anyway. So the tuples would be this, right? So that is a 4 tuple, but you would put it in parentheses, right? So this would be the first record field, the second field, third field, and fourth field, but they're all grouped together in records, right? So the solution would be and then each of the values, in theory you could use tab separation or whatever, but it's going to be more correct in the way that this is set up, right? So these would be 5 tuples, right? But you would separate the fields with commas. So that would be what I would expect for that. And then, let's see. So a directed graph, you remember that these relations are given in source and then destination, right? So you would create a graph with 4 vertices, right? And then you would start from vertex 1 and go back to vertex 1, right? So that would be a loop. And then here you would go from source 1 to destination 4. Here from 2 to 3, and so forth. And so I understand if you're a little bit intimidated in terms of how to do this in LaTeX, but you will be given an example in the solutions that I post here in a little bit, so that you can mimic the source for how to generate those graphs. And then here, given the relation on this set, right? So to set A1 through 4, find the symmetric closure, right? So so here we want the missing pairs, right? The missing ordered pairs
delta. So what I'm searching for is delta, right? So that the union with it gives the relation, right? So you can say I'm looking for the the boundary that is missing here, right, on something that would be symmetrically closed. Right? And so again, I'll include the results in the solution. And I was going to show you that there are online compilers, right, for how to do this. And so we have a solution for merge sort in both C and Java included in the lecture notes. And so here, I allow you to pick a language of your choice. So I'll tell you now, the bonus on the exam, it will be implementing merge sort, but in a language of my choosing. So you'll have to translate it into some other language. And so I encourage you to use something like Rex Tester, right, whenever you're coding it to make sure. So you don't have to install it on your machine or whatever. You can write the code online, and then you can run it, and you'll get your output here. Right? So I'll include, I'll implement it again, and I'll include the solution when I post the solutions to the review. Hopefully no later than tomorrow. We saw how that worked for the review questions, right? But I'm way over on my time, so I need to finish this up. I had hoped to go through the entire exam, but the lecture for the first half took a little bit longer than I was anticipating. But I will post solutions, and you can use the tech file from there is kind of this launching point to help you work through the problems, so you can get the bonus. The bonus for the exam, if you submit your work with LaTeX and PDF, will be 5 points, right? So you could get a score up to 110. Okay, so that's it. Good luck in your preparation. Have a good weekend. Don't stress too much. You'll have plenty of time. And if anything is unreasonable, you'll also have plenty of time to ask me about it. And we have a couple of class periods to go through. There won't be a lecture on Tuesday. I'll just post the exam, and you can get started on it. But the next lecture will be next Thursday. So, all right, have a great weekend, everyone.